Yeah, welcome everybody to this webinar. So we have two topics today from my side: analyze coupling between two harnesses. This, I have to say, is not something new. This is not like a new approach, a new feature or something, but this is something that every now and then comes to me via support, and I see that some customers or some Feko users are having problems with this here and there. So I will just give a bit of advice here and show how it's done and how it's not done. And yeah, the second topic will be the usage of schematic link. The schematic link is a rather new feature in Feko, and it's also in the MTL world. So that is topic-wise, it fits. Yeah, it's a useful tool to have a direct connection between the MTL world and the 3D world, the full wave world. And that has been missing forever. And now it's there. So you can have your MTL cable constructions, and then you can have a direct connection, like you would intuitively connect your cable with your objects, right? And this is now doable. I will show you how. Okay, let's start with the outline. This is what I already said. Still, I have a slide, all right? Cable coupling, and then I will demo everything, and then the schematic link feature, including the demo, and that's about it. Okay, let's start. Coupling between two cables. And of course, I have prepared everything, so I will open the first model now. Will probably take 7 or 8 seconds. Here it is. So this is the reference model. So this is a MOM model. There's no MTL included. It's a very simple example. Of course, it is. We have two wires or single conductors. When it comes to cables, it's not a wire, it's a single conductor, right? And the single conductor has some insulation all around. And the two single conductors are connected to ground, and one is excited and the other is passive. And yeah, that's that's the MOM model, and I will take the result here as reference. I'm interested in the coupling between port 1 and port 2. Port 1 is this one, and port 2 is at the end of the other cable, which is somewhere here. So this is port 2. Cable 1, by the way, is terminated by 50 ohm at the end. Cable 2 is not. Okay, so the frequency range is 1 megahertz to 1 gigahertz, quite a wide frequency range. Of course, I'm using continuous interpolated range here because I want to save time, and in most cases, you can have quicker results when you use this instead of like this one, where you have like 101 frequencies or something, right? This can also make sense here and there, but in many cases, this is the better approach. So in this case, I think I cover the whole frequency range with, I don't know, 12 or 20 or so frequencies. Yeah, let's look at the results. I think I didn't miss anything here. Everything is very easy to understand, I think. So let's have a look post Feko to check the results. Here we are. So let's add a Cartesian graph and get the S matrix. And let's check S1, 2. So this is how it is. Looks reasonable. I have no complaints. I will just trust it. Yeah, let's give it a better name. Let's call it MOM. Also, I would like to have the color black in this case because I will take this as my reference. I want to compare the other results with this one. For me, that this is then the black one is the reference. Okay, now what is the MTL approach when I want to simulate this here? Different ways, of course. By the way, the distance between the cables is 2 centimeters. So they are close. So you can expect some coupling between those cables, coupling through inductance and capacitance, right? Not only field radiation. That's the important thing here. Now let's open the second model where I basically tried to rebuild the same scenario, but not with MOM wires. Instead, I now have cable paths here, cable paths, and on these cable paths, I have MTL multi-transmission line cables running. And in this first example, the name tells it already, conductores is, it's two harnesses. So in this case, and this is what some customers do, they think they have two cables, paths, two cables, so they will create two cable harnesses, like I have here. You see, we have harness 1 and harness 2. Harness 1 has a single conductor here with two connectors and one cable, and cable harness 2 just the same, right? And then in the schematics, you can see it's just like in the MOM model. Cable number 1 has a port at the start and a 50 ohm at the end, and the other cable has a port at the end. That's it. And yeah, these are, like I said, two harnesses, two more or less independent cables, but who tells me that I will get wrong results with that? Now, if I look at the results, let's add the model here. It's this one. If I add the results here, we can clearly see that it's not matching too good, right? And that's what that's why I chose, or why I picked this topic here. This is the wrong approach. If you want to calculate the coupling between two cables and you have, let's say, strong coupling because they're close to each other, it's not a wise idea to use two independent harnesses. Also, it wouldn't help if you would have only one harness and then use two independent cable paths, by the way. I will show you how you would do it correctly. So the next model, which gives nicer results, would be this one. So I now have both cables in one harness, and not only in one harness, but also in one path. And that's the key information here. It's not actually the harness that differs, it's a path. So in this case, it's only one path. So how can I have two cables having a distance in one cable path? The answer is you need a bundle. Right? If you look at my cable cross sections, this is the single conductor, and here's the bundle. And in the bundle, I just have these two single conductors, and I define the distance of 2 centimeters between them, and that's it. So this should then be very close to the MOM reference result. Yeah. Let's check the results to prove. So that's one harness, and the results are here as to 1, 1, 2. And yeah, these are quite good. So this is as close as you can get with a pure MTL. And at least I would say satisfyingly well matching. Now, another way you can do it would be using the combined MOM MTL. Combined MOM MTL means that the MTL, the multi-transition line theory, is used for the inner of the cable, and everything that's like from the shield, let's say, make it simpler, the shield itself, so the most outer surface of your cable, it's a shield basically. Or if you have a single conductor, it's the single conductor, is solved with MOM. So the MOM, the interaction with the outside world is then, let's say, more accurate, and you have much more degrees of freedom for your model setup. So let's see if I did that. Did I do that? I think yes, I have it here. So this is basically, again, two harnesses and two paths, which with pure MTL would give wrong results. But here I was smart enough to go here, double click on cable harness, go to solution and say, hey, Feko, please use the combined MOM MTL in this case. It says here only for shielded cables, yes, but also for single conductors. That's the restriction with moment here. I did it here and I did it here as well. And having a look at these results will show excellent agreement, which is not too surprising with a simple model like this. So S1, 2, yeah. Okay, if you compare MOM now with the last one, with the MOM MTL, of course, we have excellent agreement here. Yeah, that's already it for the cable coupling topic. I will now not show you the result for the 2 paths version because that's basically, it's rubbish, as they say in UK. Yeah, okay, let's switch to topic 2. Let me close several windows. Yeah, demo 2, schematic link. I consider this more relevant, more exciting, so to speak. Let's see. I have again prepared some stuff here. Let's start again, as usual, with the reference, the pure MOM solution. Takes a bit longer to open. Lots of mesh elements involved. If I zoom out, okay. So what's this? What is this? It is a piece of cable. This is a coaxial cable, how it would look if you would use method of moments for it to solve it. We have the outer shield, the inner conductor. Inside we have some polyethylene, and here on the surface we have a waveguide source. Of course, you can have other options for excitations, but in this case, it's a waveguide source. You see, it's quite finely meshed. This is necessary to have the high degree of accuracy that I will need for comparison with MTL. So in this case, MTL is the more accurate one. I have to admit, no, it's just it's a long cable and it's a wide frequency range, and that's why it's quite demanding to solve this. But yeah, coming back to the description of the model, this is the coaxial cable that ends here. Somebody took a tool and cut the cable here. The inner conductor is sticking out a bit, and then somebody went really crazy and used some copper wire to have some sort of pigtail connection here. So a very rough, not very high frequency suited connection from the shield of the cable with the ground of the PCB. So this is the simplest PCB that you will find in the universe. It's just a 50 ohm strip line, but that's not important right now. Yeah, this is, like I said, the MOM model, and let's have a look at the results. Yeah, let me just open Feko. So if I would run the simulation here, it will take several hours. I ran it this morning just for testing purposes with a 32 core, so it took 2 or 3 hours or so. Even if I use continuous frequency range. Yeah, let's have a look at the S11. Looks like this. So very well matched. Also not surprising, it's a waveguide structure, or the coaxial cable, I have to say, it's finely meshed. And also here we have a well-designed 50 ohm microstrip, so we have a very low S11. Yeah, by the way, at the end of this 50 ohm strip, there's a 50 ohm connection to ground. Okay, that's why we have basically no reflection here. So yeah, this is the reference. Again, let me rename this to MOM, so we remember this is the reference and make it black. Okay, how to have a quicker result than with MOM? We can, of course, for the coaxial cable, use the MTL once more. Let's do this. Cable to PCB MTL. That sounds like the model I'm looking for. And this looks like this. So the cable is now represented by the cable path, and along the cable path, I have this coaxial cable cross section which I have defined. It's just the same dimensions as in the MOM model, same materials. There's a shield outer, a solid shield in this case, like in the MOM model. And the MTL cable stops here because in previous versions of Feko, you could not directly connect it here, right? So now you can. And how you can do it? First step, define 2 points on the geometry just to make sure that you actually have mesh vertices there. That's an important thing. Yeah, so I just imprinted 2 points, P1 and P2 here. And so you see that the mesher automatically then creates vertices there. And then all you need to do is go to cables, and there is this schematic link feature, which I'm focusing on. And here's where you can add connections. I click here, so you can have 2 types of connections. One connects to geometry, like I would do here. I would just connect to points on my structure, or you can connect to ports. So in this case, I will not do this. I will connect to the structure. I will show you then in a second example how to connect to ports, but now let's keep it very simple. So basically just choose point and click somewhere, and there you go. Now then this schematic link appears in the schematic view, and then you can connect the pins however you like them to be. In my case, it's the pin 1 of the cable. It's the inner conductor. I want it to be connected to the pin 1 of the schematic link. The pin 1 of the schematic link actually points to this point here, P1. And for P2, pin 2, it's just P2. Yeah. So basically, the schematic link provides the connection between the MTL port and the geometry. And let's see if that works. Let's have a look at the results. Add model. It's this one. Voltage source. Yeah, looks okay at least, right? Just remember we are in the range of 0.0 something here. So it's small numbers. We have quite good accuracy here, I would say. But let's check maybe the Smith chart. Maybe it is a bit clearer there. Let me do it like this. First, let me rename this here to MTL. And I always love to have this use trace level text here. And anyway, display Smith copy like this. Okay, and we see maybe this is acceptable, but I know we can do better. So this is our reference. Let's zoom in a bit. And the MTL is a bit off. Not a lot, yeah, but still a bit. So what can we do about it? Let's go back to the model. And I tell you, I didn't know that, so I had to learn that myself. So this feature and the direct connection to geometry works, as you have seen, but it can be improved a bit. Let me open the next model, this one. So the connection is improved when you use a port for the connection, like I did here. There's some faces hidden. Let me get them back. So this is really the end part of the connector, just same as in the previous model, but with the only difference that I now added a wire port here. Sorry, an edge port. The edge port helps the solver to have the more accurate connection for the current flow into the 3D world. That's how I would translate it. That's how I would explain it. And the rest of the model is basically the same. The only difference is that the schematic link is now not pointing to geometry points like this P1 or P2. I could easily delete those points, but now the schematic link is connecting to the port. The port here is called SL core. That's the name of the port, and that's the one difference. And then there's another one. We can add reference faces. Reference faces are those which are directly connected between the negative side of the port and the MTL cable or MTL port, so to speak. This is also mentioned in the manual in case you will forget, or you maybe rewatch the video if it comes to practicing this. I will hopefully not forget about this. So the port should be defined like this. So the negative side should be in the direction of the reference, and the reference in this case is the faces between the port and the MTL. Okay, that's how to remember it. Yeah, that's how I did it. And to my surprise, the results improved quite a bit. I mean, they were already okay, but now they are very, very close to the MOM. Where is it here? So this is then this one, let's call it MTL port, maybe like this. And looking at the Smith chart, let's just make a Smith copy and disable the MTL. So yeah, this I think is good agreement. One could still then say, okay, the MOM model is probably not accurate in this case. Why not remesh the MOM model even further? Yeah, because I don't have the time. I don't have the nerves to wait for results forever. So yeah, zoom out a bit and it fits perfectly. Yeah, and I think that's all I have. Maybe one more. It doesn't make much difference now. All I did is I added a monopole here, so this works as well. Yeah, you can of course just feed antennas directly with cables now. It's not only about PCBs, and yeah, if you have an antenna and you want a more realistic excitation, including a piece of cable or something, you can easily do it now. Yeah, schematic link feature. Well done, development. Keep up the good work. And that's it from my side. Conclusions. Okay, I can repeat 3 sentences. So regarding coupling, with MTL, if strong coupling between cables is expected, it's recommended to include them in a single harness, sharing one cable path. Okay. Schematic link feature, what is it? It allows direct connections between MOM MTL and full wave. By the way, MOM MTL, not only MTL, but yeah, probably forgot to mention it. And we have learned one thing, the connection to ports instead of faces or edges with the schematic link will improve accuracy. I wonder if this is something that will still change in upcoming updates. I don't know. This is probably still under construction. It's a new feature. Thank you.